Hello friend, welcome to the course Multivariate Procedure with R. You can recall that in the last lecture we had considered the Hotelling t-square statistics and we have constructed the test of hypothesis for the mean vector in a one sample data set. In case if you try to recall earlier we had considered the t-test and we had developed it for one sample test and two sample test. In one sample test, we had only one sample and we conducted the test of hypothesis like H naught mu equal to mu naught. So, that was done in the last lecture. And then again in the univariate case, we also developed the two sample t test in which we were trying to compare the population means of two normal population when sigma square is unknown, but that is equal from the two populations. Now, the same thing I am going to do in a multivariate setup. So, I already have given you this idea that how we have developed the Hotelling t-square statistics and how do we find out the one sample test. So, now the same Hotelling t-square statistics will be developed in a two sample case in this lecture, and I will try to show you using the R software how you can conduct the test of hypothesis for the equality of two mean vectors when the covariance matrices of the two normal population or multivariate normal population are unknown but equal. So, let us begin our lecture now. So, now in this lecture we are going to consider for the test of hypothesis for the mean vector from multivariate data in two samples, right. So, we have the same setting what we have considered earlier, that we have conducted a random experiment with p random variable, and the random vector is defined as a p cross 1 vector like this of a random variable x1, x2, xp. And suppose this x1, x2, xn is a random sample from multivariate normal distribution with mean vector mu and covariance matrix here sigma, and the probability density function of this multivariate normal distribution is given by this expression, right. So, now you are aware of all these things. Now, we try to consider the test of hypothesis for the mean vector when sigma is unknown. So, in case if you recall, we are going to develop it exactly on the same lines as we have done in the case of univariate random variable, right. So, first we try to observe here random sample of size n1. So, if you try to see how I am writing it, because I have here two samples from two different populations. So, I am writing here the two samples here like this x and 1, and suppose my second sample is again x1, x2 here up to here, x of size n2. So, now in order to discriminate between the two samples, I am writing here in the superscript 1 in the first data set and 2 in the second data set, so that you can identify that we have got a sample either from the population number 1 or population number 2. So, that is how I have indicated here that x1, and in the superscript I am writing 1 inside the parenthesis like here this, right, this. So, this be a random sample of size n1 from a multivariate normal distribution with parameters whose mean vector is mu, but it is now indicated here as a mu superscript 1 inside the parenthesis, and a known covariance matrix sigma, which is a positive definite matrix. Similarly, we observe now here a second sample. If you try to understand, it is written exactly in the same way as I have written the first sample. So, this x1, x2, xn2, this is a sample of size n2, and in the superscript I am writing here 2, 2 like this. So, that is indicating that the random sample of size n2 is coming from a multivariate normal distribution with parameters mean vector mu2 and covariance matrix sigma greater than 0. And now we are interested in conducting the test of hypothesis for the equality of two mean vector, that is my h naught is h naught mu1 is equal to mu2, right. So, and you can see here both mu1 and mu2, they are the p cross 1 vectors, right. So, now what we try to do, first we try to estimate this mu1, mu2 and sigma from the given sample of data. So, first based on the sample 1, which is here x1, x2, xn1 with the superscript 1, we try to estimate the mu vector mu1 as the sample mean vector like this one. So, if you try to see, this is simply like that, sample mean vector of sample mean of each and every random variable, right? And this is based on the first sample here like this. And sigma is going to be estimated by here this S1 1 upon n1 minus 1 summation alpha goes from 1 to n1 x1 minus x1 bar transpose into x1 minus x1, right? You have to be little bit careful the way I'm trying to announce it or saying x1 in the same way. For example, when I say x1 here like this is x alpha 1 and this is here x1 bar, right? So but that we already have discussed earlier that how to understand it, right? If you try to see here, both this mu and the MLE of mu and sigma are estimated by this x1 bar and say S1, right? Do you remember that we had discussed the maximum likelihood estimation in the case of multivariate normal distribution earlier? So the same thing is being applied here. Now we consider here the second sample, and based on that we try to estimate the mean vector mu2 and covariance matrix sigma here like this. So this is again the sample mean vector of say x1 bar, x2 bar up to here xp bar, and this is based on the sample of size n2 from the second sample. And similarly this sigma is estimated by here S2, which is 1 upon n2 minus 1 summation alpha goes from 1 to n2 x alpha 2 minus x bar 2 transpose into x alpha 2 minus x bar 2. Now based on this the two estimates of this sample covariance matrix, see here S1 and here S2, we try to find out here the pool covariance matrix, and it is indicated by here capital S, which is n1 minus s1 plus n2 minus 1 s2 divided by n1 plus n2 minus 2. And if you try to recall, that is the same thing we have done in the univariate case also, where we have observed the two samples from two univariate normal populations, and we had estimated the sigma square from the two population, and then we had obtained the pooled variance. So the same concept has been extended here, and we have obtained the pool covariance matrix, right? Now based on that we try to use here the Hotelling t-square statistics, but now the Hotelling t-square statistics has to be defined for the H0 mu1 equal to mu2. Well, I'm not going to give you here the mathematical details and derivation of this statistics, but the final outcome here is that the Hotelling t-square statistics is obtained here like this. It is n1 n2 upon n1 plus n2, and then x bar 1 minus x bar 2 transpose S inverse x bar 1 minus x bar 2. And this statistics follows the F distribution in this format, that is n1 plus n2 minus k plus 1 divided by k into t square upon n1 plus n2. This follows a F distribution with k and n1 plus n2 minus k plus 1 degrees of freedom under H0. That is when H0 is true. And this is called as say this t square distribution with n1 plus n2 degrees of freedom. Well, you need not to worry for these things, because when you are trying to implement it in the R software, then you have to essentially look into the values of P, right? And in case if you want to conduct or find the confidence region for this hypothesis statistics, like as mu1 equal to mu2, which I can write down here as say mu1 minus mu2 like this. So if you want to find out the confidence interval for the parameter mu1 minus mu2, then this is obtained here like that. That the confidence region for mu1 equal to mu2 with confidence level 1 minus alpha is the set of vectors m such that x1 bar minus x2 bar minus m transpose S inverse x1 bar minus x bar 2 minus m should be less than equal to n1 n2 upon n1 plus n2 into t square with k and n1 plus n2 minus 2 degrees of freedom. Or this can be written in terms of F distribution also, that you try to replace this t square with here F statistics or the related F statistics, right? So this is how you can find out the confidence region. And as I explained earlier, because now we have here P, random variables. So this is not called as confidence interval but confidence region. And you know that this confidence interval concept also helps in the test of hypothesis. So that is why this is needed here. And you will see that in case if H0 is rejected, then the R software will also give you the outcome about the confidence interval for the individual mean components, right? So, and if you recall, I have reproduced here the slide where I had explained you that how are you going to use the confidence interval and test of hypothesis. So, we had learned that if H naught is rejected at alpha level of significance, then there exists a 101 minus alpha % confidence interval which yields the same conclusion as the test. So, suppose my hypothesis is H naught theta equal to theta 0. So, if the confidence interval does not contain the value theta 0, then H naught is rejected. Right. This is the same concept what we have used in the case of test of hypothesis. So, now we come to our aspect that how to conduct the two sample test H naught mu1 equal to mu2 in the R software. Right. So, this test requires the package MV test. Capital M, V, T are in the uppercase alphabets and others are in the lowercase alphabets. And this is the same package which was used earlier in the one sample test based on the Hotelling T-square statistic. So first you need to install this package and then you have to upload the package using the command library, and after that you have to use the command here to sample ht2. So you have to be careful that here this T of 2, S of samples, and HT, that is Hotelling T, they are in uppercase alphabets, and 2 here is numeric. So you have to be careful how do you write this thing. So this is the statistics, or this is the command which computes the Hotelling T statistics for 2 independent sample and gives the confidence intervals also. Right. And so how are you going to use it? So you have to write down here the command to sample ST2 as I explained you. Then you have to write down the data, which is going to be a data frame usually. And then you have to define here a group. So this group vector is the values of numbers 1 and 2, which are going to indicate that which of the observations are coming from the population 1 and which of the observation in the sample are coming from population 2. And alpha is here the level of significance as we have used it in the earlier, and then homogeneity is equal to true. This is indicating that the sample covariance matrices are homogeneous. That we have discussed that if the two covariance matrices are from where the multivariate normal distribution from where the sample have been obtained, if they are equal, then this is called as homogeneity. So we have to use here homogeneity is equal to true, and if you try to use homogeneity is equal to false, then that will be a case that the covariance matrices of the populations are unequal, and in that case first you have to conduct another test, and the homogeneity of covariance matrices can be investigated using the box M function. Well, I'm not going to discuss here, but if you wish you can do it. Right. So now this function is going to compute here the Hotelling T-square statistics about the equality of two mean vectors, and when H0 is rejected, then this command will compute the confidence interval for all the variables to determine the variables which are going to affect the decision of rejecting the null hypothesis. Right. So this is how the outcome will look like. The outcome will have 8 elements. The value will be here ST2, which is the value of Hotelling T-square test statistics, then F value, which is the value of F statistics, degrees of freedom, the degrees of freedom related to the F statistics, then P value will be there to conduct the test of hypothesis. Then there will be CI, which is the confidence interval, so the lower and upper limits of the confidence interval for all the variables. Then the value of alpha, that is the level of significance or the confidence coefficient, will be given. And then we will have here descriptive 1 and descriptive 2 components, which are going to give you the descriptive statistics for the observation from the first and second group. So if you try to see, this is the similar outcome what we have used in the case of one sample Hotelling T-square statistics. right? So let me try to take a similar example what we have taken in the one sample Hotelling t-square test. So means earlier we had the data only on say one sample. Now we will be considering the data on the two sample. So suppose the data on 10 persons in two group is obtained on three variables: ages in years, weights in kilograms, and hemoglobin level in HB, right? So earlier you have considered the same variable, and now I am considering here two different population from where we are going to obtain two different samples. So the data here in the group 1, it is coming from normal mu1 and covariance matrix sigma. So there are here person number 1, 2, 3, 4, 5 here you can see. So for the person number 1, the age is 10, weight is 35, and hemoglobin level is 11. For the person number 2, the age is 15, weight is 40, and hemoglobin level is 12. And similarly for the third, fourth, fifth persons also we have got the appropriate data. Similarly, in the group 2, the samples are drawn from normal mu2 sigma, and here also we have observations on 5 persons. And for example, the person number 1 in the group number 2 has age 12, weight 33, and hemoglobin level here is 10. And similarly, the person number 2 has got age 3 years, weight 42 kg, and hemoglobin level at 11. Right. So now we have here two samples, and we want to test here the hypothesis H naught mu1 equal to mu2 at a 5% level of significance when sigma is unknown. Right. So yeah, first I have to give all the data. So what I am trying to do here, if you try to see, I have defined here a variable age12. Age12 means, if you try to see here, if I try to highlight it in say black color, the ages of the persons in group number 1, they are here like this, and the ages of the person in the group number 2, they are here like this. And now I am trying to join them together, and all this data is written here as a data vector. So if you try to see here, these 5 values, they are coming from group 1, and these 5 values are coming from group 2, right? Because this is how you have to give the data, right? And the same thing I have done for the data on weight and hemoglobin level, that first 5 values, they are from group 1, and the remaining 5 values, they are from group 2. And the hemoglobin level also we have the similar conclusion, that these 5 values are from group 1 and these 5 values are from group 2, right? And now I try to create a matrix of this data set by here n row equal to 10 and col equal to 3, and data is given here by age 1 to weight 1 to and HB 1 to, and by rows equal to false. Now I try to define here a group, because if you try to look into this data set age 1 2, so you have to inform the R software that okay, first 5 values are coming from the population 1 and they belong to sample 1, and the remaining 5 values, they belong to sample 2. So for for this I define here a variable here g, like that first 5 values are going to be 1 1 1 1 1, and the remaining 5 values will be of 2 2 2 2 2, right? So for example, if I try to explain you in this data set age 1 2, so for the first observation I will say here value 1, then 1, then 1, and for first 5 values I have the values here 1 for the variable g, and for the remaining 5 observations we have the value here 2, right, to indicate that they are coming from group 2. So this is how I try to define here my here variable g. Then I use here the package library mvtest, and then I try to give here the command to sample st2 data m, that is coming from here, group is equal to g, that is coming from here, alpha is equal to 0.05, and homogeneity is equal to true, right? And now you will see here, actually this outcome will come here like this. This will be the screenshot, but since I cannot make it in a single slide, so I have divided it into 2 columns, and I will try to explain you how these things are coming. So if you try to see here, this is value here ht2. So this is the value of Hotelling t-square statistics which we have defined earlier. This is the value of here F statistics. This is here the degrees of freedom of the F statistics. The p-value is here like this, 0.01, right? So now you can see here, if you try to say here, take here alpha is equal to 0.05 and p-value is coming out to be 0.01, which is less than alpha. So your H0 is rejected. And when H0 is rejected, then this command will compute the confidence interval for the 3 variables, right? So if you try to see here that these are the, actually this part is the confidence interval, right, for the 3 variables, which is indicated by here Ci, right? So these are the lower limits, these are the upper limits, and then it is deciding whether the variable is important or not. Right. So these are the confidence interval for the first variable. You have to read it like this. First variable, then the second row is for second variable, and third row is given the confidence interval for the third variable. And how to define this first, second, and third variable? You have to just see how you have defined your here data. Say age, weight, and say hemoglobin level. So the first variable will be for about age, second will be for weight, and third will be for hemoglobin level, right? Then you have here the value of level of significance alpha. Then we have the descriptive statistics for sample 1, right? It is something like the means of the 2 variable and the standard deviation of the 2 variables, right? This is for the age, this is for the weight, and this is for the hemoglobin level. And the same thing here is for the second sample, for sample 2, right? So these are the here means of ages, right? This is for here weight, and this is for here HB level. These are the sample means of the observation in the 3 variables. So essentially, if you try to look at these values, they are trying to give you the values of the sample mean vector. And then similarly here, the second row is the standard deviation of the variables 1, 2, 3, that is age, weight, and hemoglobin level. So this is how you can see that you can conduct the Hotelling t-square statistics for the 2 sample case without any problem. And yeah, before I try to go to the R software, let me try to give you an idea, the concept about Mahalanobis distance, right? That's an important terminology, and in multivariate statistics, and this is defined as like this: mu1 minus mu2 vector sigma inverse mu1 minus mu2. So this is here mu1 minus mu2 transpose. So this is going to be of order 1 by p. Sigma is of order p by p, and mu1 minus mu2 is of order p by 1. So this delta square is going to be a scalar quantity of order 1 by 1. Right. So this quantity actually measures the distance between the 2 normal population, normal mu1 sigma and normal mu2 sigma. Right. But again, this is based on this population values mu1, mu2, and sigma. So what we try to do, that we try to obtain sample from this first population normal mu1 sigma, and from second population normal mu2 sigma, and then we try to estimate mu1, mu2, and sigma, and we try to obtain the sample version of this delta square. Right. So this statistical distance, or the Mahalanobis distance between the 2 sample points, say x, which is consisting of the observations on p variables x1, x2, xp, and y is the sample from the second population normal mu2 sigma, having the observation from p variables y1, y2, yp, and they are in the p-dimensional space Rp, that is understood. This distance, this statistical distance, or this Mahalanobis distance, is defined as the positive square root of x minus y transpose S inverse x minus y, and S is the estimate of sigma. Right. So this is how you can estimate it, and if you try to understand, there is a close connection between the Mahalanobis distance and the test of hypothesis for the 2 sample mean vector. So we have just considered the null hypothesis about the equality of 2 mean vectors as H0 mu1 is equal to mu2. Now if you try to write down here this quantity here as say mu1 minus mu2 like this, then this H0 becomes something like mu1 minus mu2 is equal to 0, right? And if you try to look at the definition of delta square, in case if the mu1 and mu2 are equal to 0, then delta square becomes 0. So, this hypothesis can also be written as h naught delta square is equal to 0. So, sometime you will see that different test of hypothesis consider delta square equal to 0, and which is the same thing as that test of hypothesis for the equality of the two mean vectors. So, mu1 and mu2, when they are same, that is equivalent to saying that delta square is equal to 0, and the same test statistic for testing h naught mu1 equal to mu2 can be used for testing the hypothesis h naught delta square equal to 0, right. So, now let me try to show you this example on the R software. So, you can see here, I will just try to copy and paste the entire thing. Now, you understand it's not a very difficult thing for you, and I already have uploaded the package MV test, right. So, if you try to see here I have given here the age, weight and your hemoglobin level of these sample data. Then I have created here a data M matrix, and this is here G. So, if you want to see here, I can show you here that how the data M looks like. It will be like here this, and G will be here like this, right. And now, if you try to use here this command for the two sample test, two samples ST2, then it is coming out to be here like this, right. Then let me try to give you this idea one by one. So, this is the value of your Hotelling t-square statistic, this is the value of F statistics, these are the degrees of freedom, this is here the p value, then we have here the confidence intervals, then we have here the value of alpha level of significance, then we have the values of means and standard deviation for the variables in the sample 1, and descriptive 2 similarly has the values of sample means and standard error from the sample number 2 data, and then it is about the test what we have used and its class, that is MV test and list. Right. So, now let us come back, we come to an end to this lecture, and you can see here that in this lecture we have considered the two sample test for the two mean vectors which are coming from multivariate normal population. Their mean vectors are different, but their covariances matrix are unknown but equal. So, and if you recall that the way we have developed the h naught mu1 equal to mu2 in a two sample test in a univariate case, this is almost the same like what we have done there. The only thing is this, now we are trying to handle the data vectors in a multivariate setup. So, all this calculation, formulation, etc., they will be changed, and so that has happened here. So, now it will be actually good if you try to review the earlier lecture on the two sample test and try to see what I have done in this lecture also, and that will make you very confident and comfortable that how the univariate topics are converted into a multivariate topics. Well, it is not straightforward, because for example, the way the distribution of Hotelling t-square statistics is found, that is quite different than the way other distributions are found, but the basic concepts are the same. So, now my request is that you try to take some data set and you try to practice it in the R software. My suggestion will be that you try to generate two samples from two different multivariate normal population and try to keep their mean vectors almost close or say different, try to change the covariance matrix in all the cases, right, and then try to see that how it is happening when it comes to the decision from that test of hypothesis. And you will see that okay, the variability in the covariance matrix is also affecting in some way to the test of hypothesis. So, this type of practice will give you an experience or a hands-on experience that how the data speaks and how you have to understand. So, you try to practice it, and I will see you with the next topic on scaling in the next lecture. Till then, goodbye.